Plane mirror reflection follows a few simple rules. The distance of the object is equal to the distance of the image. The height of the object is equal to the height of the image. Object placement decides whether you can see the image. From this perspective, we can only see the object. Light cannot travel from the object to the mirror back to the camera. To see the image, you have to look at it. This line of sight creates congruent angles of incident and reflection, creating a path from the object to your eye. To prove an image's location, we look at it from two different perspectives. This ray diagram highlights all of these big reflection ideas. These two reflected rays only appear to cross behind the mirror, so this is a virtual image. The James Webb Space Telescope, set to launch in March 2021, will use plane mirror reflection to take images of distant objects. Light from the planet, star, or galaxy will reflect off gold-coated specular plane mirrors. The light reflects off a mirror at the end of the telescope to create a focused image. Light comes straight in, but it needs to reflect off the mirrors and hit that central mirror at the perfect angle. To create this change in angles of incidence and reflection, the 18 mirrors have to be angled proportionately. The James Webb Telescope's little brother, the Hubble telescope, focused light in a different way. To proportionally change the direction of the surface, Hubble used one large curved mirror. NASA engineers designed the mirror so that they could predict how light would reflect off it to create consistent images. Let's explore how curved mirrors use circles to predict how light focuses. This mirror is 80 centimeters from the point at the bottom of the screen, and this object is halfway between the two. The point at the bottom acts like the center of curvature of a large circle. As I place other mirrors in an 80 centimeter radius around this center of curvature, a curved mirror starts to form. It takes some adjustment and smoothing, but a pattern starts to form. When parallel light enters the mirror, it seems to reflect and shine back on the object that's halfway between the mirror and that center of curvature. The light is reflecting or focusing on this point, so we call it the focal point. The light converges or comes together in this concave mirror. It's called concave because the shape of this mirror resembles a cave. The curved reflected surface is on the inside. Lasers make everything a little clearer and a lot cooler. As light enters the mirror in each direction, it reflects back to the focal point. This is because angle of incident equals angle of reflection, but the surface is consistently curving. The challenge with science is that you have to be able to reproduce it. For this concave mirror, the center of curvature is 50 centimeters away because this circle has a radius of 50 centimeters. The first concave mirror had a focal point halfway between the center of curvature and the mirror. Since this mirror has a center curvature of 50 centimeters, the mirror should have a focal point at 25 centimeters. As light shines on the concave mirror, it seems to create the same pattern. The light reflects back to that focal point, which is located halfway between the mirror and the center of curvature. The concave surface creates varied angles of incidence and equal angles of reflection. The consistent change in the surface consistently reflects light to the focal point. If we placed an object like a fork in front of the mirror, we would still need two rays to prove the image's location. Light travels straight from the top of the object and reflects through the focal point. If that light travels from the top of the object through the focal point, it reflects straight back out. Where these two reflected rays cross, the top of the image would appear. This would create an inverted or upside down image. Since the rays of light appear to cross in front of the mirror, this is called a real image. Real images are projectable. If you place the object inside the focal point, you would produce a virtual upright image. If you placed it at the focal point, the image disappears. Because I used a bunch of plane mirrors, my concave mirror isn't as smooth or polished as it should be. Neither was the Hubble Space Telescope's mirror. Due to a hairline imperfection in the curvature of their concave mirror, the telescope had to be retrieved and repaired in outer space. The mirror suffered spherical aberration. In other words, it was not smooth and curved in the way that it created a defined focal point. It was an inconsistently shaped mirror. Now that we've explored concave mirrors, let's understand the big ideas. The focal point is always equal to half of the center of curvature. Due to the shape of the concave mirror, light converges, it comes together at the focal point. The focal point is in front of the reflective surface, so the focal point is positive for concave mirrors. A concave mirror can give you three options depending on where you place the object. The first is that if you place the object on the focal point, you'll have no image. If you place the object inside the focal point, you'll get a virtual upright image. This is an image that would appear behind the mirror. If you place the object outside the focal, then you'll get a real inverted image. This is a projectable image that would appear outside or in front of the mirror. On the focal, no image. Inside, virtual upright. Outside, real and inverted or upside down. Those are your three options. The opposite of a concave mirror is a convex mirror. This convex mirror still has a center of curvature of 50 centimeters, but the reflective surface is on the outside. When you shine light on it, it creates a new pattern. Instead of converging and coming together, the light rays reflect away from each other and spread. When light spread, it diverges, so convex mirrors diverge. The focal point is half of the center of curvature for curved mirrors, in this case 25 centimeters. However, with a convex mirror, the focal point is behind the reflective surface, so the focal point is negative for convex mirrors. This mirror has a focal point of negative 25 centimeters. As light diverges off the convex mirror, it does not focus on the focal point. Instead, the focal point helps guide the direction that the reflected rays travel. If we place an object, we can identify and locate its image. Light from the top of the object travels straight to the mirror and reflects away, using the focal point as a guide. Light from the top of the object can travel toward the focal point and reflect straight out. Because these two reflected rays could never touch, a convex mirror will always create a virtual upright image. Convex mirrors are also based on a circle, but the reflective surface is on the outside, not the inside. That same observation follows. The focal length is equal to half of the center of curvature. The center of curvature is the same as the radius of the circle. As we can see in this diagram, the light diverges. It spreads out as it reflects off the outside of that convex mirror. Because of the shape of the convex mirror, the focal point is negative because it's behind the mirror. The light diverges using the focal point as a guide. Convex mirrors are always going to give you the same image, virtual. You may see these virtual upright images created in warehouses or around the corners in driveways. This handheld mirror has a convex side that diverges light and a concave side that converges light. The convex side always creates a smaller upright virtual image. The concave side creates an inverted virtual image when I'm outside the focal point. For concave mirrors, when the object is inside the focal point, the image is virtual and upright. At the focal point, the image seems to disappear. If the object moves beyond the focal point, the image inverts and becomes real. As light reflects off the concave mirror, it consistently focusing light 5 centimeters in front of the mirror. As the parallel light reflects off the convex mirror, it diverges or spreads, consistently spreading light away using the focal point that's 5 centimeters behind the mirror. You can explore this at home. Go grab a big spoon. The convex side will always create an upright virtual image. On the concave side, as you move the spoon closer to your face, you'll see the image go from real to non-existent to virtual. Now that we have a deeper understanding of mirrors, use this digital lab to explore the relationship between distance of the object, distance of the image, height of the object, and height of the image. For each scenario, you'll place the object at a certain location, make it a certain size, and record the other information that's given in the simulation. Enter your data into the Google Docs and complete the calculations and questions based on your data and observations.